the second film on ultrasonic measurement systems. The first film we had an introduction before we talked about the piezoelectric transceivers. This film will cover piezo or principles for ultrasonic transmission before we go into some examples. And if we have sound that goes from one material to another, like material 1 here and material 2 here, the materials are specified by something called a characteristic impedance, Z. The impedance has something to do with the resistance the sound meets and how it's delayed and so on. If we send from one material to another, some of the sound will go through and transmit into the new material, while some will reflect. Very much like light behaves when it meets an interface or a boundary between two materials. If you, for example, send light from air to glass, some will reflect and some will transmit through to the other side. Now, if the characteristic impedance of the two materials is the same, then everything will transmit over to the other side. Nothing will reflect. That is the case, for example, if you have iron and steel. And the higher the difference between the two, the higher proportion is reflected and less is transmitted. And here's a table of some specific materials with their characteristic impedance. And air, water, tungsten, epoxy, aluminum, and PZ37, which is a piezo crystal. So this is just an example, and you see also that there is a relation between the impedance and the density. A very low density gives a very low impedance. So when we create or make piezo transceivers, you have the active region is here. This is where you have the piezo crystal, and then you have here the blue region here and the gold region, the gold colored region. They are the electrodes, so that is where we connect our source. You have an acoustic absorber at the which sees that there as little sound as possible goes backwards in the wrong direction. Then you have something called acoustic matching layers, and the matching layers, they make sure that the material that this transceiver is connected to matches in terms of impedance, which means that as much energy as possible will go through and as little as possible will reflect back to the piezo crystal. And then you connect this one to the material, which maybe, for example, can be steel. This means that for us, when we buy an ultrasonic transceiver, you need to be careful, because if you buy one that is supposed to be connected to air, you cannot use that in water. And if you buy one that is supposed to be used in water, you cannot use it in free air or in steel. So you have to make sure that you buy one that is meant to be connected acoustically to the material it's designed for. So the one you have in your drawer may not be suitable for your application. And the applications may be, for example, here ultrasonic flow meters. We have talked about a few of them last week. You can have sonar, which is basically a range finding, so you can use ultrasound to determine the distance between the transceiver and some object. You can use it as a proximity switch, which means that you can find out if there is an object or not in the path of the ultrasound. You can use it for flaw detection, which means that it can discover cracks, for example, in a pipe. You can use it for medical diagnostics. Here is from a pregnancy where you have a child inside the womb of a woman. And for example, for indoor positioning systems, this could be used for examples with patients with Alzheimer or something, that they can find out which room the patient is in, because inside a building GPS is not very useful.